Welcome to Info Next. Today we're doing CAP's 1997 Part B's question 3. So a spherical balloon of radius big r equal to 5 centimeters has within it a small solid lead sphere of mass m and radius r. The mass of the balloon is negligible as compared to the mass of the lead sphere. The system is buoyantly neutral, floating just below the surface in a pool of water. The balloon is given a light downward push. Describe the motion of the system qualitatively as quantitatively as possible. And now we have a hint. A spherical object of radius r moving without turbulence and with a velocity v through a fluid of viscosity eta experiencing a retarding force given by the Fv equal to 6 pi r eta v, right? And these are some constants we need to know. So first, let's sketch out the situation. So we know just a pool of water. Let's make it really deep. Water here. We know there's a balloon here, right? It says here, spherical balloon. It's a small lead sphere of mass and radius r. So this means there's a small, dense sphere made of lead inside, right? This is r. This is big R. Now I want to find, first we want to find the mass of the small sphere, right? And the radius of the small sphere. So in terms of your radius, big radius. So we know it's in a buoyantly neutral system, right? So the F buoyant must equal to mg, the weight of the entire system. You know, F buoyant force is just going to be equal to density of the liquid times the volume of the liquid displaced times g, right? So now we can know the volume of this is just going to be 4 over 3 pi big R squared, right? Big R cubed, I mean. And now we know the rho is going to be rho of water, density of water, and times g. This is going to be equal to the force of gravity acting on, right? So Fb goes upward and Fg goes downwards. They have to be equal for it to be buoyantly neutral. So that is equal to m times g, right? Because the big balloon has no mass, so this is only lead sphere. Now with this equation, we can rearrange for m, because we cancel out the g's. We know this constant, we know this constant, we know these, so we can solve m. So we get rearrange for m, we get m equals to like 0.52 kilograms, right? Now we can solve using the density of lead to solve for the radius of the ball. So we can say that, you know, mass is just density times volume, right? So we can equal to density of the lead ball times 4 over 3 pi r cubed equals to your mass given here, right? Now I can solve this and you get r is equal to 2 centimeters, right? So let's think about what happens when you give this a push downwards, right? So if this goes downwards, there will be more pressure exerting on the balloon, so the balloon radius will shrink, and it will shrink, so then the buoyant force will become even less because r becomes smaller, right? So the force becomes even less. So the gravity will be bigger than the buoyant force. So continue to go downwards even more, right? There's also going to be drag force here, but it's going to still go downward more. So I want to see it's going to reach a terminal velocity, right? When the balloon has shrunk so much that the radius is equal to your radius of the lead ball, right? So that's right equation there. So you get mg is still the same, equals to rho and then 4 3 pi r cubed times g. Right? You can see these are clearly not equal, right? So they're not reached terminal speed yet. But then after this acceleration, right, you also have to consider the drag force. So this is going to be a minus 6 pi r, let's see, 6 pi r eta v, right? So this is going to be equal after a while. So the velocity reaches the point where these cancel out to be equal to mass, right? So now we can solve for v, right? Because we know everything. So mass, we can express this in terms of pressure, in terms of, density and radius, right? So now mass is what? Mass is 4 over 3 pi r, big R, right? Big R cubed times rho and g. And put this on the other side, we get minus rho 4 3 pi small r cubed times g is equal to 6 pi r eta v, right? So then we can just solve for velocity. We know these values, right? And we know the radius and the radius because from the top, given all your constants. So we can solve that velocity is equal to around 13,000 meters per second. And we can also do some further analysis using the Reynolds number. And the Reynolds number is Re, right? It's defined by the density of the fluid, the velocity of the fluid over the viscosity of the fluid times the distance diameter of the pipe it's flowing through or something. So we don't know this diameter, but we know these three values, right? You can plug in, this is really big. So this is much larger than 4,000